Okay, so we've learned that the derivative, so that's our new word, derivative of a function f of x, which we denote by f prime of x, so we have like a little apostrophe there that we read prime, a prime of x, or dy dx, and that's really to stress the fact that this is change in y over change of x. This represents the slope, is defined to be the limit as h approaches 0 of f of x plus h minus f of x over h. So the derivative itself is a function, and it represents the slope of the curve, slope of the tangent line for any given value x. So we're going to start with an example here. We want to find the derivative of f of x equals x squared plus 1 at x equals 2. And so our goal is going to be to plug in to that limit formula. We're trying to find the derivative is that limit. So I find that the best way to approach this in a sort of methodical way is to start off by finding all of the different pieces of that limit formula. Well, I already have f of x. F of x is given. F of x is just x squared plus 1. So really, the first thing that I want to do, actually, is find f of x plus h. And honestly, you should simplify it if possible. So find f of x plus h, and if possible, simplify. And so I say honestly like that because you don't have to do this here. It just kind of makes sense to have it simplified before you stick it into that limit formula. It's going to help make the step a little bit cleaner, a little bit easier to follow, and have less to do when you already have it big inside the limit. So if f of x is equal to x squared plus 1, f of x plus h would be what happens when every single time I see x, I replace it with x plus h in parentheses. Okay, so we really don't want to forget those parentheses. They're super important because whatever I'm doing to x, I am now doing to x plus h, which means if I'm subtracting x, I'm subtracting all of x plus h. So in this case, I'm squaring x, which means that now I'm replacing that x with x plus h squared and adding 1. So now the thing that's being squared is x plus h. Now it says that we should simplify if possible, or if there's any simplification to do. There is. I need to expand that x plus h. So this is equal to x squared plus 2xh plus h squared plus 1. And that's going to be my f of x plus h. Now be careful about this as well. Remember that x plus a squared does not equal to x squared plus a squared. I can't distribute powers. So what I'm doing here with that x plus h, I'm going to do it with an x plus a, is saying that this is x plus a times x plus a, and I'm foiling here. So I'm doing first, outer, inner, last. And that's what gives me that 2xh that I have in the middle over there. Okay, so that's that. The next thing is I'm going to stick it in the limit. F of x plus h minus f of x over h. So here, the next step is put into the limit and use one of the 3 0 over 0 techniques to evaluate. And the reason I say that, well, why don't we just take a look at this inside of the limit and then you'll see. So we're going to have the limit as x approaches, as h approaches 0 of f of x plus h. That's what we found in the first one. So x squared plus 2xh plus h squared plus 1 minus f of x. So that's the thing that we have highlighted up there. So that's my x squared plus 1. Always, when you are subtracting, put in parentheses. We're going to be distributing that minus sign. And then all of this is divided by h. Now, before I simplify, before I do anything, let's plug in h equals 0. We have the limit as h approaches 0, which means that the thing we're plugging in here is h. So I'm not plugging into x. So on top, I'm going to get x squared plus 2 times x times 0, that's 0, plus h squared, so that's 0 squared plus 0, plus 1 minus x squared plus 1 in parentheses. So what I have there is x squared plus 1 minus x squared minus 1, and all of that is over, plus 1, sorry, plus 0, 0, sorry about that, over 0, and that gives me a 0 over 0 when I replace that h with 0. That is always going to happen, and it makes sense that that's going to happen because if we think about this in terms of the secant lines and tangent lines that we used to develop this, we started with 2 lines, so we were able to calculate that slope. But then, with 2 points that allowed us to calculate the slope. Then we moved that point on top of the other point, and now we only have 1 point. So we can't calculate the slope. So it makes sense that we're going to end up with 0 over 0. It's going to happen every single time with the limit definition of the derivative. We know we're going to get 0 over 0, which means we know that the factor that we're trying to cancel out is h. Be careful. Can't cancel those. That's a bad plan, even though I see those h's there, because I have a whole bunch of plus and minus on top. Remember, we can only cancel if it's all multiplication and all multiplication. So if it's h times things, not h plus things or minus things. So here this is h plus things or minus things, so I cannot cancel those out. So my goal is to find a factor of h. So h is multiplied by things. And I'm going to start off by distributing that minus sign. So this is h approaches 0, x squared plus 2xh plus h squared plus 1 minus x squared minus 1 all over h. And check it out, those x squareds cancel out and those 1s cancel out. So now I have the limit as h approaches 0 of 2xh plus h squared over h. Now you'll notice here that there is a factor of h in both parts of these things. So it's 2xh plus h squared. In other words, the greatest common factor of the numerator is now h. So I can factor that h out. And what I have left is 2x plus h over h. Now those h's cancel out. Goodbye. Goodbye. I've canceled out the problem, and I have the limit as h approaches 0. There's nothing left on the bottom, so there's like a 1 on the bottom, which I don't have to write. 2x plus h. I plug in 0 for h, not x, and I get that the answer is 2x. So only h gets replaced with 0. So then what I have is that f prime of x is equal to 2x. This is the derivative of the original function. So this is the derivative of f of x is equal to x squared plus 1. So this is a function that for whatever x value I plug in, it's going to give me the slope at that x value. So this particular question said at x equals 2. So our third step, only after we've calculated, we will plug in the given value if a value is given. If asked, I'll do this in green again. If asked to evaluate at a specific value, plug in. Okay, so if you're asked to evaluate a specific value, which you will not always be, plug in. In this case, we are, so I'm plugging in 2. So in other words, what I want is f prime of 2. And I'm just going to go back to the top to remind you, that's because that's what the question asked you to do. It said, find that derivative at x equals 2. So now I'm plugging in 2. F prime of 2, and I'm plugging it in to that derivative function that I got. So that is 4. 4 A number, not a function, is the derivative at the x value too. Which means, just FYI, to remind you that this is the slope of the curve at x equals 2. And if we wanted to draw a little graph just to see that, our original function was x squared plus 1. So that's like this happy parabola, x squared plus 1 at 2. Here's this point 2, 5 when x is equal to 2. If I draw a tangent line here, so in other words, I remind you, a tangent line is just a line that briefly grazes the function and is going in the same direction as that function. That's that 4. The slope of that line is 4. And that's it for this problem. Head on to the next video to see another problem where we might have to use different limit techniques.